Hi, I'm Kyle, and this is Lab 3, Black Hole Orbit. The goal of this lab is to calculate the mass of a black hole. In the following problem, a star is orbiting a black hole of unknown mass. The position data, x and y coordinates, time step in Earth days, mass of the star, and position of the black hole are given. Using the results of my analysis, I estimated the mass of the black hole to be 2.9835 e to the 31 kilograms. I used VPython code and Newton's second law to calculate the mass of the black hole. The physics principle used was Fnet equals dp over dt, because you need Fnet in order to find the mass of the black hole, which we will get into later. But for now, we will figure out how to calculate Fnet. Using the position data given, we have two positions which we can use to calculate a velocity, and with three positions we can calculate two velocities. With two velocities we can calculate a change in velocity. With change in velocity times mass equals change in momentum, and change in momentum over change in time gives you an approximation of Fnet. And we continue to do this over and over and over again, and we can calculate many Fnets using the VPython code. The Fnets should and was the same number throughout the loop. It was constant because the only thing acting on the star was the black hole. Here is a picture of the star's motion. I chose the star as the system and the surroundings as the black hole. Since the black hole is the only thing acting on the star, Fnet points towards the black hole. The parallel portion of Fnet, or dp dt parallel, is in the same direction as the motion of the star, or the tangent line of the circle, the orbit. And the perpendicular is Fnet minus the parallel portion. Now here we're going to calculate the mass of the black hole. Now with Fnet given after the code is run, we use this equation, Newton's law of gravitation. Fnet equals g times ms mv over r squared. And we rearrange the variables to get mass of the black hole equals Fnet times magnitude of r squared divided by g times mass of the star. And g is the gravitational constant, and in order to get r, I used the position of the star minus the position of the origin. And the position of the origin was the position of the black hole, and I calculated this number as the mass of my black hole. Conclusion. What does it mean? Fnet versus change in P over change in T. Change in P over change in T is an approximation of Fnet because you're using finite numbers and timestamps. Delta T, which in this case, which was 86400 seconds. Fnet actually equals dp over dt, and that dp over dt is a derivative, which would mean delta t would have a limit of 0 instead of 86400. And so with a limit of 0, you can actually calculate what Fnet is. But because we can't do that, we have to settle for approximating Fnet. What if? If the black hole was replaced with another black hole and the motion of the observed star remained unchanged, you cannot tell the difference between the new black hole and the original black hole because the mass would be the same. If the motion of the observed star remained unchanged, that would mean the Fnet would be the same. If Fnet's the same, then mass would be the same. If mass is the same, then you really couldn't tell the difference between the two black holes, because obviously we can't see black holes. Yep. Thank you for your time, and have a great day. Bye!